Thank you. Thank you. Hello, everyone. So yes, there will be. So I will discuss the there were different possibilities. I was planning maybe to either to continue an NV magnetometry, but this is a rather specialized topic maybe. So I decided to switch a little bit and to discuss the question of the coupling of NV to nuclear spins. You will see that nuclear spins have somehow two influence on the NV centers. First, a drawback somehow, because they will set the limit, the practical limit for the T2 time in the sample. And that's really important. That's of course very important for all applications. But it can also be a resource. You can especially do NMR on the nuclear spins using nuclear spins in the diamond, and use the NV centers as a kind of ancilla to address the nuclear spins in diamonds. So, and this is the experiment we're going to see this afternoon. So basically, we will have then in the afternoon two presentations by my colleague, Léa Lachaud, who is an assistant professor, and Pierre Grégoire, who is a PhD student. So Léa will do a demonstration about a very student NMR system, which is commercial, that it comes from the US, from a company named TeachSpin. And basically, the nice point with that system is that you can really see everything. So it's not, you do not do accurate NMR with the system, but what's very interesting is that indeed you can really, it's a hand-on system, and we can easily demonstrate Rabi oscillations, spin echo, those kind of basic things on on liquids. Okay, so she will do the demo. That will be something like in between half an hour to 1 hour if everything goes well. And then we'll switch the topic, and this is more something that we are working on at the moment, which is addressing nuclear spins in ensembles. And you will see both the experiment, you will see how we address the single spin. I will explain it this morning, but you will see all that, I hope, in real life, and you will see the Rabi oscillation on the nuclear spins and how we control them. And I will explain briefly this afternoon why we are working on that and what we want to do with this system. Okay, so as I mentioned, we can measure the coherence time of the NV center by the scheme of Ramsey fringes. So the Ramsey fringes is, and actually you will see this system in live this afternoon. We will prepare the NV in MS equals 0 state, for instance, and then we apply a pi/2 pulse at a frequency that is resonant, for instance, with a transition from MS equals 0 to MS plus 1 or minus 1 by applying a small magnetic field that removes the degeneracy between the plus minus 1 level, so that we can address one or the other of the two transitions. And then we wait after this pi/2 pulse. This pi/2 pulse has put the block vector, for instance, on the x-axis of the two-level system corresponding to this transition. And then this system now will process around the magnetic field that is used to specify the quantization axis and to remove the degeneracy between MS plus minus 1. And at the end, what we do, after this free precession, we apply a new pi/2 pulse, and this pi/2 pulse should bring the system should be equivalent somehow to a pi pulse if there's no decoherence effect. We measure the population in the MS equals 0 state by applying now a new laser pulse. Okay, the scheme that we mentioned, we discussed yesterday. And if we now look to the photoluminescence intensity, which is measured during this time window for the integration, this time window here, this is the time window here, that we will measure the photoluminescence intensity, and we modify the duration between the pi over 2 pulse, the free, during which we had the free precession of the spin. Then what we observed is those kind of fringes. There are fringes at approximately at the Larmor frequency, and at the same time, there is a decay, and the decay is associated to the fact that we have all these spins see different effective magnetic field with slight modification, and we can this induce this decrease of the signal on a time scale of T2 star. If it's a single spin, then it's the jitter that will produce this effect. So if we now continue that, in practical, in CVD grown diamond, the T2 star is about 2 microseconds recording, and this is limited actually by the bath of the nuclear spins of carbon-13 that exist in the diamond. Diamond consists of two natural isotopes, either carbon-12, which exists at about 99% abundancy, and carbon-12 has no nuclear spin, so somehow it has no influence. And on the other hand, there's 1% of carbon-13 impurities, and those nuclear spin will have an influence on the NV centers and will create the T2 and the T2 star. And this is discussed in this paper by associated to the thesis of Anaïs Dréau 10 years ago. Okay, now we can, and this has been discussed also by many, many other people. So there's a way now to increase the coherence time. Actually, yes, you have somehow two possibilities. The first one is to get rid of the carbon-13 impurities and to grow diamond consisting only of carbon-12. And this can be done by CVD. You inject in the plasma methane that is made from carbon-12 atoms. And from that, there is a very, very high increase of the T2 star time, because now it reaches 100 microseconds. And this is very important for all applications of NV centers. The other approach is called dynamical decoupling. So somehow you will have different kind of pulses excitation that will, sorry, I should put it here, because that's a slide that was expected to be here. Sorry. Okay. Okay, that's the slide. So what we can do, for instance, is to circumvent the fluctuations of the magnetic field of the bars, and this can be partially done by, for instance, the spin echo technique, where we apply a pi pulse between the two pi over 2 pulse. And you will see, for instance, in the two experiments this afternoon, that indeed it increases a lot the time during which we can control somehow the precession of the spins. And that makes a little bit the measurement scheme more complicated somehow, but what you see is that the survival time of the echo, which is now limited by the T2 time, the intrinsic coherence time of the signal goes up to 500 micrometers. So there's, for instance, a strong enhancement factor associated to that, and it can even reach higher values depending on the system. Okay, you have a lot of sequence that can be used for dynamical decoupling, like CPMG, XY8, all that. All these sequences of pulses have been designed by for magnetic resonance purposes. So basically, you just take a book of nuclear magnetic resonance, and you can find all those sequences well described and how they can be now implemented in this scheme for adapting after that to the given measurement you want to do. This is the value you can reach with these complex decoupling time is at the end limited by two parameters, not anymore the spin fluctuation of the bath, but the T1 time so this means the time at which the NV will come back to the thermal equilibrium, and also to the interaction with phonons in the matrix that you cannot really compensate with this scheme. And the T2 is about 2 milliseconds that you can achieve, the kind of limit that you can achieve. And if you now go to lower temperature, the T2 increases a lot significantly just because somehow you freeze all those interactions. First, the thermal equilibrium you get the T1 is increased by that, and also the interaction of the phonon that can destroy the coherence of the NV centers is also smaller. So then you reach values that are about a second at those low temperatures. So that's quite interesting also for possible applications. Good. So the question now, after this, we want to discuss the question of coupling to nuclear spins. And the coupling to nuclear spins, basically, we will now focus on the coherent coupling. And this coherent coupling is due to the hyperfine interaction. And let's first discuss the intrinsic coupling that exists in the NV centers. It is the coupling between the nitrogen atom, nitrogen 14, that has a nuclear spin n equal I equal 1. You can have nitrogen 15 also, as I mentioned in the first lectures. In that case, nitrogen 15 has a nuclear spin of 1/2, which perhaps makes analysis a little bit easier, but it's not the problem. The point is that nitrogen 15 only exists at a very small abundancy, so you need, again, a very specific engineering of the NV. For instance, if you create the NV by ion implantation, then you use nitrogen 15 gas to implant the ions, and then you will have these nitrogen 15 in the bath, in the system, associated to the NV. What's more interesting for us is really we'll stay on nitrogen 14. So basically now we take the Hamiltonian is a little bit more complicated because we have to add this new degree of freedom. So the Hilbert space somehow, the Hilbert space that we measured, that we discussed before for the NV electronic spin, plus now, and we add product tensor, the Hilbert space associated to this spin. So the Hamiltonian now writes the following way. This is the one that we already discussed for the NV centers, including, for instance, the coupling to an external magnetic field. And now we have all these terms that I will try to discuss. So these terms correspond first. The first one is simply, as you can directly see, the interaction of the nuclear spin with the external magnetic field. And they're just now to the gyromagnetic factor, gamma n, associated to this nuclear spin, taking into account the nitrogen 14 nuclei. That's the first term. So it's the external influence. And of course, for instance, if we consider the influence of the magnetic field, we know from the first lecture that this will be 1,000 times to 2,000 times smaller than the influence of the magnetic field on the NV electronic spin. Then there is this term. This term is a quadrupolar system. And this is a little bit perhaps more complicated, but somehow if you have this quadrupolar term exists if we have a spin which is different than 1/2. If it's 1/2, somehow it's something that is independent, where you do not have that term. For spin 1, you have this term, but somehow that can be integrated somehow in the full Hamiltonian, as we will see. It's just a shift of all these levels, but not. And then we have something which is important. So it's what we call the hyperfine tensor, and the hyperfine tensor has different components. Basically, it consists of two things. The first point is like when you do in atomic physics, you know that the electron, for instance, can go very, very close to the nuclei. If I consider, for instance, the atomic hydrogen, on the 1s transition, on the 1s state, the ground state it's the orbital, the 1s orbital, the electron has a strong probability to be on the nuclei. There's not a zero probability to be on it, which makes that somehow there is a very strong coupling between the two-wave function, and that's called the Fermi interaction. Okay? So we have the same kind of thing here. We will have the Fermi interaction, and we also have the direct magnetic dipole-dipole interaction between the dipole of the NV and the dipole of the other system. So when you have that leads to a tensor form of the hyperfine interaction, and basically this tensor form has two terms. One which is longitudinal. This will correspond to an interaction between the two spins that are aligned, and another one that is perpendicular, which corresponds to the interaction between spin up for the NV, for instance, and spin perpendicular for the nuclei. So now you have to consider and to go into the details of that. In the case of the NV, with the coupling with the nitrogen atom, the nitrogen atom is very close to the NV electronic cloud can be very close to the nuclei of the nitrogen impurity. So this makes that the interaction is very strong between the hyperfine interaction is very, very strong. And somehow you can demonstrate, you can show that you have at the end, using secular approximation, or you only conserve the resonant term, the term that matters is the longitudinal coupling. So somehow the Hamiltonian will be fixed by this. So if you take that into account, what does it mean? If I consider, for instance, one level for the NV, which either ms equals 0, ms plus 1, or ms equal minus. Now I had this parameter, and I see now that I will have the interaction term will lead to a degeneracy that is removed. Here I will have, for instance, let's put it like that. Okay, so -1 for the electron and mi. Okay. But when I take into account this term here, acting on this effect, of course, now it removes the degeneracy. And the degeneracy will depend on the value of ms and of mi. Okay, so for instance, that level will now be split into 3 components and separated by an energy difference, which is just A parallel, the hyperfine interaction. Okay? That occurs both in the ground state, and we know that we have the same spin structure in the excited state, so we have also the same structure in the excited level. So what I have at the end is, for instance, triplet state associated to the different values of mi, the quantum number for the nuclear spin, and then all my optical transition, taking into account that Hamiltonian and taking into account all the things that we have already said about the NV, cannot change the nuclear spin value. So you have a selection rule that tells you that delta mi is equal 0 So somehow, all the electronic transition that the NV centers can do will not change the other value of the parameter. So what I have then, it's now, I will see the line is going to be split into 3 components. And each of those components is separated by the value of this parameter. So it's very simple in the way. And we have here, in this value, is about 2 megahertz. Okay? So if we now look more carefully about that thing, I can show you this system, and I will come back to that later on. That's for the nitrogen spin. For the nuclear spin, it's much more complicated. You have somehow 2 types of coupling to NV. You have first carbon impurities with carbon-13 that are close to the NV. And in that case, they will shift. There will be this hyperfine interaction. But it's more complicated than what I have said, because somehow the interaction is not strong enough, and you cannot do the secular approximation. So you have to take into account the full tensorial component, tensor component of the coupling. And that's a little bit more complicated somehow. But at the end, what you have, it's again now each system. So for instance, that system now, you add a third Hilbert space somehow, which is associated to the carbon atom, to the carbon nuclei to which the system will be coupled. Carbon nuclei have a speed 1/2 for carbon-13. And then we have now 2 peaks that appear associated to the 2 quantum state of the carbon nuclei, and separated by the interaction, the hyperfine interaction associated to the coupling with the NV center. Okay? And you can continue with that. So there's really a big manifold. So you can now have another interaction with another carbon atom, like this one, for instance, and that will again produce new 2 states, et cetera, et cetera. And at the end, you can have a huge amount of those spins. And up to now, for instance, the record of identification of all these coupling to nuclear spin was, I think, done in Delft in the team of Tim Tamino. And they are able to label something like 20 to 30 nuclear spin, and being able to address them independently of that. Of course, at one point, you're limited by the T2 star. The T2 star somehow will erase all that structure, and you will just, average all that structure, and now you will simply have just something in which we cannot distinguish anymore this individual coupling. And now you see, after this frozen core somehow, you will see now the other carbon impurities acting now as a bath of the nuclear spin that provide the T2 star. They are too close somehow that you cannot, that they mix up, and at the end that creates a decoherence time. So you can have very nice simulation about those effects, and that's done just in the paper I mentioned before. Okay, so these are typical spectrums. So you see, for instance, if we start with the carbon-13, we have this 3-peak structure on a single NV. If I now had as another resource the coupling to 1 carbon-13, you see that now each peak is now split into 2 components, as I described before, okay, due to the hyperfine interaction with this nearby carbon nuclei at around 1 megahertz. And if I continue like that, I can add now another nuclei. That's a second nuclei, which is maybe at a longer distance. And this coupling will now produce another 2 couplings like that, et cetera, et cetera, et cetera. And as soon as my lines are narrow enough, I can try to distinguish all these pairs and try to map where they are somehow located in the lattice. And this exploration was done by Anaïs in her thesis. So she measured more than, she recorded the hyperfine spectrum on more than 100 single NV centers. And after this large ensemble of data, she could somehow classify all these coupling to nuclear spin into different families. Each you have the number of NV that corresponds to the coupling with one hyperfine, with different hyperfine coupling, as you see here. Here by adding that, we have this complex structure that you see. Here now we have separation of 4 megahertz, et cetera, and you can see, sort out the different structures. That was really a beautiful work she did. And after that, up to a point where the hyperfine now become too small, and somehow then you cannot distinguish anymore, you cannot separate, resolve all these individual interaction between the NV and these different natural impurities. And now, somehow, after that, it's a bath, okay? This tells you, the message here is somehow that really there's a lot of things that can be done by addressing all these multiple nuclear spins. But for that, somehow you need another, something more. In all these experiments, of course, we do not have a single-shot experiment, but you can implement ways to address this nuclear spin in a way where you can, using the NV measurements, you can do single-shot measurement on these coupling. That's very nice too, but perhaps too little bit too complicated for what I wanted to explain here. But you can do a lot of things on these using these nuclear spins. So one thing I want now to discuss, and this will be related to the experiment we will see this afternoon, is how we can transfer the NV spin polarization to the nuclear spin. And for that, we will use something which is called, we will use crossover. So this crossover between different resonances, the mixing between the MS state can occur when there is a crossing between their energy. So let us consider, here, for instance, what I plot is the energy here as a function of the magnetic field, of the B field. Okay? So what I have here, there is a dependence, and as I mentioned before, here we have a difference of about 3 gigahertz, and here we have a difference of about the same, but about 1.4 gigahertz. So now, and for some reason, the MS equal plus minus 1 level in the excited state are lower in energy than MS equal 0 state, but that's not so important. And you can observe this line at 1.42. So what happens now if I apply the magnetic field? If I apply a magnetic field, what I will have is here a crossover between, so a crossing between MS equal plus minus 1 and MS equal 0. Somehow, if these states are not coupled, it's not a problem. They still live independently, and it's not a problem that energy coincide. This we'll call the S-slack, okay? And it occurs for a magnetic field at about 510 Gauss. I would have the same effect, I should have plotted here, by plotted here, okay? This is the G-slack, somehow you put E or not, or G-slack, and this occurs at 140 Gauss. Okay? And this can be very computed. It's just the standard calculation of the Zeeman effect that you do for a magnetic field perfectly aligned on one axis, on the axis of your NV center. And we'll see also later on what happens if we are not aligned, the B field is not aligned. Okay, now what we have, it's suppose we would have only the crossing, only the interaction between A parallel, SZ, IZ, okay? Then there's not this crossing again is not a problem. There's no mix. Cannot produce a mixing between the different states. What happened is that here I have the coupling. I should have changed the notation. This is the coupling A perpendicular. The coupling A perpendicular will mix now the state. Okay? It mixes a spin, electronic spin up together with the perpendicular component of the other spin. So what happens in that case? Suppose we have a magnetic field far from the S-lag. Basically, the systems are well separated in energy, and somehow our good basis is ms on one side for the electronic spin and mi for the nuclear spin. They don't mix. You agree with me? Okay. Now I am at the S-lag, at the S-lag. At the S-lag, we have this crossing. At this crossing now, sorry? No? So at the S-lag, there is a crossing. And in that case, we are like in a coupled two-level system. Here, the influence of the perpendicular hyperfine coupling will mix the state. Okay? So now I am not anymore in this good basis. I am in a basis that combines all those states. Okay? So I am in the basis plus minus that, depending on the strength of the interaction, will couple 0 plus and plus 1 minus. Okay? This is for a spin 1/2. Huh? I wrote that for a spin. So this was written for ms for s equal 1 for the NV, and I equal 1/2 to simplify. Suppose it's nitrogen 15, for instance. It could be the same for nitrogen 14, and we'll see it, but we just have to write it down more carefully. So now I have this mixed state at this crossing. What happened then? So far from the tuning, I can somehow consider the ms equals 0, ms equals 0 state, and I'm not able independently. So as I apply green laser, with a green laser, I polarized in ms equals state. In the ground state, I go to the ms equals 0 on the excited level, but this electronic transition does not have any influence on the spin, on the nuclear spin. They live in different space. They are not coupled. Same now if the nuclear spin is either up or down. So all optical transitions have no influence on the nuclear spin. It's completely different now if we are at the G-slag. At the G-slag, so I can have those transitions, okay? 0, that case. You agree with me? So what happened with that? What happened with that is that I can go now, as we know, due to the mixing of sorry, I should write it down here. Let me see like that. Yes. Yes, no. Let's put it. Let's consider this. Now I consider this. We start from here. This state. Sorry, I should not consider this. I start from here. 0 and the spin up for the nuclear spin. Okay. I go to the excited state. Delta ms equals 0. So I keep that quantum number equal to 0. This one, I suppose, it has no influence during this transition. But when I'm in the excited state now, I am on the mixed state. I am in this situation. So in this situation, there can be now a flip exchange. Okay? So this flip exchange can turn 0 into 1 due to the interaction that I have here, like this Rabi oscillation as before. And at the same time, it will flip the system into the other thing. Okay? And now I am here. if I'm here, what happens then? I decay from ms equal 1 to the other system. I can decay. So suppose I will not have any splitting here, but I decay to that state. And this decay through the singlet channel won't change mi. So I'm in 0, now the spin down. So during this process, due to the mixing in the excited state, I've been able to flip-flop the nuclear spin. Once I am here, then if I'm here, nothing can happen. I have transition from here to here. It's 0 down, and it will come back with 0 down, because it cannot leak to the ms equal 1. Okay? So you'll see that after a few cycles, okay, the time, what I simply need is that this interaction is strong enough that during the lifetime of the NV in the electronic state, I have a strong probability to have this flip-flop to spin exchange between the electronic spin and the nuclear spin. It's the only condition. You need something that the hyperfine interaction is strong enough so that during the 13 nanoseconds where that the NV will spend in the excited level, we will have this flip-flop occurring. It's a condition. And indeed, it's what happened. The condition, due to the strength of about a bit of the hyperfine interaction, you can do some small model, a toy model of that, and convince yourself that indeed this will be a very efficient polarization scheme. So I have now a scheme that allows me to transfer the optical polarization from my spin ensemble of NV, only electronic spin, to the nuclear spin that are initially, of course, equally populated between spin up and spin down due to the small energy difference compared to KT, to the thermal energy. And that's very efficient because now I can address this electronic spin, this nuclear spin, in a similar way as what I will do, and this will be the demonstration of the experiment we'll show this afternoon. That scheme was actually invented a long time ago, due to the spin exchange, to polarize, for instance, many many atoms using, for instance, optical transition. It's the basis of optical pumping in vapor, where you have that scheme that can work very, very efficiently. I will just show you, for instance, how it works, and hopefully I will hope to be able to show you this afternoon the results. We have here these two transitions. Okay, separated by this detuning of 3 megahertz, with taking into account the different situations. So we have now the two components here, and when I scan, so it just is just the hyperfine splitting between an NV and a nitrogen 15 of nuclear spin 1/2. If I now close to one of at the slack, applying this magnetic field of 500 Gauss, you see that now this peak disappears, and that peak now is increased just due to the polarization transferred to the spin polarization of the nuclear spin. Okay, and if now I apply a stronger magnetic field, I cross the slack. You see that this effect by a magnetic field of 800 Gauss, you see that now it has disappeared, and I see again the two components of the hyperfine structure. And this was first observed by Vincent Jacques during his postdoc in Jörg Wartrup team, and it was well also described in the thesis of Anaïs. So just to show you some result that can be obtained with the hyperfine coupling, now with an ensemble of NV. So this is exactly what you will see this afternoon, just a spoiler. We have here now the magnetic, we apply a magnetic, so it's an ensemble, you will see, a highly doped system. The quality crystal with NV, about a few ppm of NV in the sample. But the quality is high enough so that the T2 star somehow is high enough so that we can resolve the hyperfine line. So we'll see these hyperfine components on each of these lines. And first, this is an off-axis magnetic field. So what you see is the 4 families of NV associated to the different orientation. And each family is split into these 3 components. Okay? As I mentioned before. The splitting value is the same. Now what I will do now, as you see here, I'm going to apply the magnetic field on one NV family. And what you see in that case is that there is now already the spin polarization that starts to appear, because you see now that there is a much stronger line that starts to appear. And this is due to the fact that we start to channel the spin population into one given state of the MI of the nuclear spin manifold. And this occurs only for the family that has its axis aligned with the magnetic field that is applied. And now we can use that to tune exactly and optimize step by step this effect. And for the other family, basically, we don't see at all this effect. You see that we keep the same number of the same values for the 3 components. And basically, all the differences that you see between these different components are certainly due already to some spin polarization that is occurring due to the specific alignment that was chosen for the applied magnetic field. There is, you may say, I have a strong difference between this side and this side, which is the 2 Zeeman components under the magnetic field that is applied. We believe that this is only an artifact due to the fact that when we scan the frequency, this is a rather large frequency range in the scan, and certainly the efficiency of the microwave excitation in the antenna will change. So we certainly have a more efficient microwave excitation here compared to here. This means that somehow the Rabi frequency for the electron spin is higher here, which leads to a higher contrast observed on this line compared to this line. But this is exactly the same family. Okay? And now here we only have the 3 families where our magnetic field is aligned on one axis. Of course, the projection on the 3 other families is identical. That means that all the other peaks now have been assembled into only one set of resonance. Okay? So this is what we're going to see, I hope, this afternoon. And now we will have then to optimize it so that we see that. And again, this is now very, very nice, because after some optimization, somehow you end with that. And when you add that, you can quantify that above more than 90% of the population is actually transferred to a given MI state. So the nuclear spin polarization is higher than 90% with that. It's difficult to do better than that on this signal, but we will show in the afternoon how we can, after that, go optimize the nuclear spin polarization using another trip. What's also important is that now you can really play with the nuclear spin. You even can forget somehow to do any ODMR scheme. You can remove your microwave signal and only play with the excitation of those nuclear spin that can be manipulated using a radio frequency at about 5 megahertz due to the difference of J factor between electronic spin and nuclear spin. Why? Because, of course, now, as we have this transition, we somehow reproduce the polarization scheme that we have. So we have bounded, we have linked somehow a given value of MI to a given value of MS. Okay? So if MS equals 0, this will be bright. So MI equals 0, or this one, for example, or MI plus 1, this will be linked to MS equals 0. And this will be since it is ms equals 0, it's a bright state. So I know just by that if I have a strong luminescence, the system, the nuclear spin is on ms equal +1. On the other side, if now the system is on the two other quantum states, I cannot discriminate them, but I know that they are somehow associated to ms for the electronic spin is equal to ±1. Okay? And this is less dim state, as I show here. So you don't have to do any kind of manipulation on the electronic spin. Just record the intensity coming out from the NV centers, and it's directly a signature of the quantum state for the nuclear spin. And now, using that, for instance, what I can do is I can do spin resonance. So nuclear spin resonance, NMR, really, as we do before, but now acting on the nuclear spin. And what's very important is that now the nuclear spin coherence can be very long. You will see that. The T2 star, as I mentioned before, it's a few hundred of microsecond in very optimized sample. If I take any kind of sample for the nuclear spin, this is much, much longer. It's in the millisecond range. So I can store somehow the information for longer time in this resource that provide the nuclear spin. And so what we do here is simply recording the population, the photoluminescence intensity, when we scan the frequency for different magnetic field. And this is the color is maybe this bar has to be commented. Color corresponds to a given magnetic field. Okay. So here, for instance, the magnetic field is as a value above the S-slack, 510 Gauss. This will be the S-slack. Okay. And here we are far below the S-slack. So what do we see? We see that somehow we have. This is the NV resonance, and the NV resonance is the nuclear spin resonance. The nuclear spin resonance, when we scan the frequency, is maximum when we are exactly at the S-slack, approximately at the S-slack value. But there is nevertheless a rather large width over the magnetic field, so it's not so difficult to find one once we have some degree of freedom on the magnetic field amplitude to observe this effect. And what's also interesting when we are here is that we see some dip here, and these dip are associated to the coupling to a spin exchange with the electron spin of nitrogen atom that exist in the sample and that were not converted into active NV centers. And we have this spin resonance that can occur, and actually if you zoom it, by doing a very, very narrow, by a very slow scan, you see that actually it consists of lot of very small, very narrow resonance that are associated to all these nuclear spin, to all these electronic spin to which the system can couple, and somehow destroy the coherence of the efficiency of your exchange process between the NV spin and the nuclear spin. So what I wanted to show you here, it's really that there are a lot of things that can be done using this trick of polarization exchange between the spin ensemble and that. Unfortunately, somehow, the limit of that is the fact that we have only one spin. We have only one nuclear spin per NV centers. And for some application, you may want to have more and more nuclear spin. So for that, you can say, okay, can I transfer the same scheme to, for instance, the carbon-13 impurities? And unfortunately, it does not work because the efficiency of the coupling is too weak between the nitrogen NV center, the NV center, and the carbon-13, so that when you are somehow in the excited state, during the decay time it has, you do not have a strong probability to have the spin flop that I discussed previously, which is at the origin of the transfer of polarization for the nuclear spin. So you have to rely on other mechanisms. And other mechanism it exists. It's called the Hartmann-Hahn transfer or echo or procedure. And this is a little bit subtle in the fact that somehow you take into account the fact that when the NV will precess at the Larmor frequency, this Larmor frequency has to be resonant with the spin difference, with the frequency difference for the carbon-13 nuclei. And somehow you can have this transfer. You can see that this Larmor precession will create a magnetic field that will create the magnetic resonance on the nuclear spin. So it's a kind of double exchange with that. But it's less efficient, unfortunately, than what it does. There's nevertheless a lot of work that is also happening, trying to optimize that, especially, for instance, by Fedor Zhelezko in Ulm. And that would lead to something quite nice. Suppose now, if I'm able to do that, then I can do something fantastic for nuclear resonance imaging, for instance. I can have now, suppose you would have a crystal and you polarize very efficiently the NV. That's not difficult to do. Just send a lot of grid light on it. And then using this trick, you transfer the population to the carbon-13. But now there are other possibilities. Also, you can, once you have this nuclear spin of the diamond, and you can put a lot of carbon-13 by, for instance, growing with methane enhanced in carbon-13. Then what you can do is now polarize again, by the same trick, a gas. And once you have a gas, or the species that you want, or the liquid you want, and then you can do NMR on that liquid, for instance. That would be much, much more efficient than the one that can rely only on the difference of population. So it's a way somehow to optimize the nuclear spin polarization by using somehow the diamond doped with NV as a resource, and then progressively transferring to the system. And what's remarkable is that the nuclear spin can have a such long coherence time at low temperature that you have now seconds, even minutes, even hours where you can do it depending on the structure you can characterize. And so you would have something which would be fantastic for any kind of application of relying on magnetic resonance of spin, because it would provide you a handle to do efficient nuclear spin polarization using the NV as a resource somehow for that. So there's a lot of work that can be done, and I'm sure that in the next year there will be really a breakthrough along all those directions by optimizing. It's quite difficult, very challenging, because you need to optimize all the crystals, all that, and to optimize also very well the transfer of polarization, but there are continuous progress on that. Okay, so I think this maybe it's a little bit short for today, but basically it's what I wanted to discuss with you for today. After that, there's a lot of things that we could cover, but I tried also to have a set of papers that somehow will give you also, by discussing this paper, some view of other application of the NV centers in parallel of what we're doing. So what I propose is that we stop here for the tea, and we can have, if you want, some time to discuss the lectures that I gave and see if you would like to comment or to ask questions, and I will see if I'm able or not to answer. Do not be shy. You can ask any question you want. If I don't know, I don't know. Thank you a lot for your attention.
All right, so let us thank you for okay, let's take a break for this.
Oh, I should have seen that. Okay, but maybe I show that in the afternoon. Yes, you will see the experimental setup just before we do it. Okay, and Pierre will show you in real time to what it corresponds, because like that it's a little bit complicated. So we will.
There is one more request for him, that the demo experiment he doesn't want to show on live, so we will just record, but no live.
Yeah, because if there is that put too much pressure on the on my colleagues. So when they have to tune everything, if you know that this is it's not. They say no, which I do understand. So, but can be recorded. It can be put after that on the jam, and no problem. But just getting it on live, no. Okay, thank you.